Debería estar grabando. Sí. Okay. So good afternoon, everyone. Welcome to our IPARCOS seminars. Today, I'm pleased to introduce Dr. Almudena Prieto. Almudena did her PhD at TISA, International Ultraviolet Explorer and Observatory, and started working at the Space Telescope European Coordinating Facility in Garching. She has been project lead for the end-of-life calibration of the X-ray instrumentation of the ROSA satellite at Max Planck Garching. Then at TISA, faculty responsible for defining and implementing the service mode operation of the VLT. Later on, she became coordinator of the active galactic nuclear studies with adapted optics instrumentation at the Max Planck in Heidelberg. Since 2004, she is principal investigator of the international project PARSEC and the Spanish principal investigator of the first adapted optics instrument project GTC, FRIDA. She joined the EIC as senior astronomer in 2006 and as of 2020 is associate scientist at the Munich University Observatory. Today, Almudena will present on the topic, the parsec view of star formation in galaxy. So thank you very much, Almudena. The floor is yours.
Okay, thank you, Enrique. So, I will try to give you an overview was reduced view of star formation in the center of galaxies. And I wanted to start by saying that this forms part of the PARSEC project, which is a multi-wavelength investigation of the center of galaxies at parsec scales. The center of galaxies are very rich environments. There are many things happening there. Star formation is one of the major processes. Accretion, the black hole activity is another one. We tackle both research lines, very interesting in the project. And I'm going to focus exclusively in star formation, circumnuclear star formation in this presentation. Just to say that the galaxies that we study in PARSEC are not selected by anything in particular. Any galaxy are very well known, are nearby because we had to achieve these PARSEC scales. Anything that's bright, and we can sample it at PARSEC scales across the electromagnetic spectrum is one target more in the project. So there are quite a number of them, not that many, because you have to keep this idea that we wanted to keep the PARSEC scales. But overall, we get inside the project galaxies of any type, quiescence or active, morphological type, whatever comes in. The idea is that we cover, that's important, a wide wavelength range possible, the widest we can. Always a consistent scale, parsec scale, so that we sample always more or less the same region across the spectrum. So for star formation, I wanted to start with this galaxy, M51, and we are not including that, this object, but M51 of any other spiral galaxy is a very good source of studying star formation because they are everywhere in the spiral arms and are very well spacious. As you see, all these red nodes. I don't know if you see the cursor. Do you see the cursor?
Yes. Okay.
Okay. So you see all these red nodes around. These are H2 regions. You see the obscuring filaments of dust that coincide with molecular gas. You see atomic gas. So you see a lot and can do a lot of physics by studying the spiral arms. And it's well spaced. So, and there is a good census of regions because there are many. But as we get towards the center, things become, as this galaxy illustrates very well, complicated because there is more light, the mass increase, and the light of the bulge behind blind us for seeing anything that is behind. So we to tackle the center and to see whether a star formation, this spiral arms event, that was always had been my quest, whether continues towards the center with similar type of morphology, then you need obviously angular resolution, and you need also the infrared. Is a very important thing because there is a lot of dust here. So this is a sample of a number of few of the galaxies we study, where we have the star formation in the nuclear region, typically the kiloparsec region, where we see them. And yes, I wanted to emphasize again that there are different activity in the nucleus. There are very active nuclei, as this one. It has a nuclear ring star formation, which is very active, as this galaxy 7469. Or we have this galaxy NGC 253, which is the prototype starburst galaxy. Is very close, so we can study in great detail, has been exhaustively studied in the literature. But the nucleus is very quiescent, so it's a dormant black hole at the center. But there is still enormous a lot of star formation here. Okay, so I will focus or describe three objects, the ones that we have studied best. That was one of the first we studied, NGC 253. I will go to this one, 1097. You see 1097 is a completely different environment from this one, and a very rich circumnuclear region of star-forming clusters of star-forming regions, hundreds of them, while here we have only a few of them. The scale are also different. We are here in the kiloparsec central region. Here we are in the 100 parsecs central region. And this is 1087. The circumnuclear ring is well known as the prototype also, circumnuclear young stellar ring in galaxies, because it's so bright and luminous. And I will go finally with this one, the last one. This is a much weaker circumnuclear star-forming region. You might notice a little dots here. It's much fainter. It's a kind of a stream from the other two that I just will discuss. But again, in the kiloparsec ring. And I will try to put in context with the properties I'm going to derive, very basic one, simple. Compare with star formation and young star formation in our Milky Way, which is where we know the best, which is also a different environment completely, because it's through the disk, spiral arms, etc. So I will start by 253, NGC 253, the prototype starburst galaxy. And well, you see it's extremely rich as M51 of plenty of H2 regions across the disk of the galaxy, or the little red dots, plenty of dust, filamentary all around. The very central region is equally dusty. This is an optical space telescope image of the center, with plenty of dust, filamentary as well. You see the bright little points here are the young stellar clusters. Many of them probably are obscured by the dust lanes here. The center of the galaxy somewhere, it was confused in the literature where the center of the galaxy was, with the analysis that was done by Juan Antonio Fernandez Ontiveros. We found that the dynamical center is somewhere here, but there is no counterpart, any optical counterpart of the center of this galaxy. We only know where the star clusters are. And below, here I put the center, is the cross, are an image of the galaxy combined VLT and adaptive optics from the VLT in the infrared. And by including the infrared, then we unveil quite a number of clusters we could not see in the optical. We have more than 3 times the number of clusters by just simply looking at the infrared and having the angular resolution as well in the infrared. This is a nearby object, and then we could get scales of 2 parsecs in which we could resolve these little tiny points here. And it's the only case where we really could measure the size of the cluster. It's about 1 parsec and a half. In the other cases that I will show after are farther, and then the size, we only get upper limits for the size. The size is important, but this is the only case we could make it. So how we characterize these clusters? Well, here you have the view again of the central region. This again, 150 parsecs or so. We put in circles the different clusters we have. We have like a 37 or so in this tiny 100 parsecs region. And per each of them, we could build a spectral distribution separately, so with no confusion, because the angular resolution that goes from the mid-infrared, this last point here is 20 microns, up to the optical, which is here on the right side of the plot. 2 microns is around here. From J band, 1 micron is all diffraction limit from the VLT, so we have very fine scales. And we have, unfortunately, no UV because there is a lot of extinction in this cluster, so no way to detect them. So we had to live with what we have. You might see already from the spectral distribution, this is in flux, that it goes down towards the UV. The UV should be somewhere here. And by seeing all these SCDs, all these spectral distributions, you see there is quite homogeneity among them. They are all very similar. And this is nice because it tells us that the ages of these classes are very similar. And in fact, from we do the analysis, we get that the ages of these clusters, as I put it here, in the range of 3-4 million years, a very narrow range. And then this narrow range allows us to measure something very important, which is the duration of the burst of each of these, how it's produced. And so it has to be very short. The time scale between one cluster and another is not much different between 1 to 2 million years. So we can estimate the best duration of these clusters in the range of 2 million years because of the narrow range of ages we measure. We measure masses of these clusters from the same analysis. Is why, well, normal, 10 to the 5, 10 to the 4, 10 to the 5 solar masses. This is a bit massive, but we have clusters of this type and this age in our Milky Way, so nothing special about it, okay? We could measure the density directly from these clusters, each of them, because we have the size. We measure the size, is 1.5 parsecs. We have the mass, and so we get densities of number of stars per surface. Each of these clusters is about 10 to the 4. Well, it's a number that is very similar to what we get in clusters in our Milky Way disk, similar ages. Or no, it's a common density, let's say, of mass in clusters. We can infer the star formation rate, but at cluster level, which is my favorite way of seeing how star formation rate should be measured, because cluster is the basic unit where star formation occurs. So it's where physics happen. And so that we can do it because we have the mass of the clusters, we have the best duration, 2 million years, so mass divided by burst. The best duration is the star formation rate. And it's about 10 to minus 2, it's a small number, 10 to minus 2 solar masses per year. Well, this is about the same star formation rate you also measure in clusters when it's studied in this way, individually, clusters in our Milky Way for the same type of mass, the same amount of mass. 10 to the 5, 10 to the 4, you get this star formation rate. Usually star formation rate in clusters in our Milky Way goes from 10 to minus 3 to 10 to minus 2, depending on the mass of the cluster. So we are in line with what we have in our Milky Way. This is a cluster level. Of course, one would say to be more in line with people usually measure in center of galaxy or in galaxy in general, star formation rate global is complicated because global means perhaps different populations. I will discuss a little bit that with the next object. But here we can do it because we can simply measure all the clusters we have in the region. We have the mass of all these clusters. The burst duration is the same for all of them. So the global, what I call the global star formation rate in the region is about higher. It's about 1.2 solar masses per year. Give us a bit the feeling of activity in the central region in 100 parsecs, 150 parsecs or so. Well, this is not much different from the Milky Way in the disk, but it's over kiloparsecs distance. It's about, we are 40% lower. But this again is in a very compact region compared to the Milky Way. Okay, maybe in the Milky Way, the way star formation rates had inferring the Milky Way over large distance, over time scales, one has to be a bit careful, but we are not much different from numbers that we get for star formation rate in the Milky Way disk, despite this very different environment and different scales. Okay, that is from the prototype galaxy, prototype Star Wars galaxy. Now let's go to this 1097 for the prototype star forming ring, very super study in the community. NGC 1097 is a different thing from the previous case. It's more early type galaxies, a little bit older than the previous NGC 253. We see a phase on, so that is an advantage because we see in the center very well how the star formation is, which is this bright source here. Is outstanding, is overwhelming, is the maximum, the brightest region here in the galaxy is the center part, which coincides with which is the star forming region. So there are star forming regions everywhere in the everywhere, no, mostly in the large design spiral arms, not in the disk, but the brightest by far is at the center, okay? In the very, very center, there is an active nucleus moderated, but the ring surpasses the brightness of the nucleus of the galaxy. One see these filaments of dust here. I will make a bit emphasis on how the distribution of dust is in the galaxies we study. Here we have a dust lane from the north, coming from the north of the disk, another one from the south, and they go straight away to the circumnuclear ring. One feed from here, and another one feed the circumnuclear ring in the center. Here there is an entrance here and another entrance here. We'll see a little bit better in the next image. The same field of view seen in molecular gas is in the center. So you see that the dust lane is followed very nice with the molecular gas. We see, as expected, dust molecular gas go together. And we have some molecular gas along some of the spiral arms where we have a star formation regions as well. Not much with star formation, we know, but it's not much along the dust lanes. But at the center is where the density of molecular gas is obviously very high. So no wonder that we have such an intensive star formation region and not much in the other parts of the galaxy, in the disk of the galaxy, because there is no molecular gas, and we need molecular gas to start forming stars. So how is this region, the nuclear region, resolving the molecular gas? That is the next image. Here is the molecular gas. Here is in ACN, but in CO is very similar. It's forming a ring. You might see the ring is split in different clouds here. The center is also molecular gas. This is the active nucleus, the moderately, but here is there. And the molecular clouds in which the ring is formed. And if we go in the optical, then we have the star forming region as it is well known, with all these little dots here and there everywhere in the ring, the same way that are here, then is populated with the clusters. There are hundreds of them. And they have different colors. And this is different colors because there are different populations. I will show you now how we get this, which is a very different situation as just the case we saw before. Before, we distinguish a coeval, one single population of clusters, the 150 parsecs or so. But here, we do not have one. We have several ones. And I'll show you now. Plus, you might notice I said nothing before. Within each of these molecular clouds, close to the peak of the molecular cloud, there is a bright source, or one or two sources. Okay, these are nothing to do with any of the clusters are here. These are thermal infrared objects. They are point-like sources only seen in the thermal infrared. No counterpart in optical or near infrared. And we think, because we are in the where the molecular cloud is more dense, we attribute this clouds, these sources, to protoclusters. So our regions are ready to probably below the zero mean sequence of stars, are heating up, ready to start to fuel hydrogen, and then we'll start to see them in the optical, but not yet. So this is a protocluster population. Together is a new, further generation of clusters that will come together with the current active ones that we see. So how do we characterize them, the clusters? Properties, basic properties, pues as I said before, we get per each of them the spectral distribution. And here we can go from the UV here in this plot all the way up to the mid-infrared or near-infrared in particular here. Okay. So you might notice that I pointed out a spectral of different points just to illustrate the different appearance of the spectral distribution. So this is a much flatter and with a shallow slope towards the longer wavelengths. This is among the oldest clusters we see in the ring. And here we are an intermediate case, no? It becomes the optical and UV becomes a bit more flatter, so it's an intermediate age, about 30 million years, okay? I had to say that we have no much problems with the dust to identify these clusters, even though that you might see there is plenty of dust intermixed with the clusters. But the clusters are always on the other part, and we are looking at the infrared as well, so we uncover plenty of clusters from the infrared. But all what we have here, or we have dated, we have a counterpart in the UV. Okay. So just to put in framework what I said before about this big dust lane that was crossing the galaxy, the dust lane is this obscuring structure we see here getting into the ring, and the other one is here. This is the dust lane I was saying. We were coming from kiloparsecs distance from the disk, the outer edge of the disk of the galaxy. And in between, you have plenty of these filaments that are intermixed with the clusters. Some of them we are even very close or in the filaments itself. But there is no mass obscuration of the filaments per se, because we estimated it from our dust maps too. So the histogram of ages, which is what I was going to focus, is like that. We have a very young population of 4-5 million years. Anywhere in the ring are all these blue points that we have here. Over the kiloparsec, you can find it anywhere. They are mixed with the older ones. This is another burst that happened in average about 30 million years ago. You find it everywhere in the ring. And even an older one, 60, 90 million years, that we could identify. At least we have that. Probably there are more, but the identification separation in ages as they get older are getting more complicated. So maybe there are more, but to be safe, at least we have these major peaks of star formation, plus the protocluster population that is coming here, but the active ones will be here. Okay. So again, for the very young burst that we have, you see there's a very narrow spike, means that the clusters ages are very similar between one and another within the burst. We can again say that the duration of the burst is very short, around 2 million years or so, for the bulk of the clusters that we have formed. We can say about the mass is a little bit lower than in the previous case in 253, but okay. We have these clusters as well, this mass in the Milky Way, nothing special about. Sizes, we only can put an upper limit, the radius less than 4 parsecs, that is all what we can say, that's it. The star formation rate at cluster level in each of the clusters. Well, as before, we have the mass of each of these clusters. We have the duration of the burst, 2 million years. So we get a cluster star formation rate, which is a little bit lower than the former. In the former case, it's about factor 5. Well, you just go factor 5 because the mass is also a bit, is a factor 5 lower. And since the time duration of the burst is the same, the only thing that is scale here when you measure the star formation rate is the mass of the cluster. So this is a little dependence with the mass of the cluster. Okay. And again, as values you find in clusters of similar mass in our Milky Way. If you want to get a bit of global star formation rate idea of not only a cluster level, but along the ring, then we can go to measure the current burst, of course, not over the whole population, but the current burst, the 4 million years. And again, we can count it. We just count the number of clusters. We have the mass of each, we sum up, all form at the same time. Well, then, of course, the star formation rate global in the ring, measuring at the current burst is just about 1 solar mass per year, which is factor 2 below what we measure in the Milky Way. But again, Milky Way disk over kiloparsecs distance. The Milky Way is several kiloparsecs. This is over the kiloparsec region. You could imagine that the values that are coming in the literature could be any number, very different of what I'm putting here, simply because people integrate the light of the whole population, okay, or the light of the ring. Either you use the UV or you use the infrared, the various calibrators you might have, or you use the H-alpha as well. Well, the point with that, I think, is very misleading to do it that way, because now we know that this is not a single population. This is a multiple population of bursts. They cover 100 million years, so at least you have to say over the scale of 100 million years how the star formation happened here. But not even that, because if we can sum all this mass of the cluster that are here, but over what duration we had to infer the star formation rate. And you cannot say, well, the whole duration of the clusters we have here are 100 million years, but that will be like measuring a continuous star formation rate, which is not the case. It's bursting. Star formation happen and stop, happen and stop, happen and stop. And there are periods of time where we have much less activity of star formation or no activity in the ring. So we can, at best, we can mention what is the youngest star formation rate in the ring, but we had to think of other ideas to measure globally because it's bursting. And so it could be periods of time when there is nothing happening here. That is the misleading problem that you might have where or you don't have enough resolution, you sample many regions, or you simply integrate the light in this particular region of the ring. Now I'm going to go with the last one I wanted to show you, this one, 1386. This is, as I said, a much fainter object, much fainter star formation rate and number of clusters, and clusters are much fainter also. The galaxies much early type than the previous cases, so it's very smooth. This is the optical image. You see a lot of filaments of dust, but not really very obvious star formation in the disk of the galaxy. As well, we don't see this large scale spiral like in the former case. This is not definitely NGC 253 with plenty of star forming regions across the disk of the galaxy. But common for all of them is there is a lot of dust in different ways. In the former case was the dust lanes. Here we have this dust lanes in a bar, which is a way to transport material to the center. But here we don't have an obvious bar, but we have this filamentary structure circularizing along the disk of the galaxy. And not much obvious star formation at the center, in the disk. In the center is not much obvious either because it's very faint. So if you zoom a little bit with angular resolution, what happened in the very central region, you see much better the network of filaments of dust that we have here, plenty all around, and somehow circularizing and forming a kind of, I would say, yeah, circularizing around the center. Even you might even follow them crossing the very central region. So they are like a draining of material that we can follow from kilopasses distance, and at the center we see how they converge towards the central region. To see the clusters is not that obvious. Maybe you might see some little points here, bright here. These are the young stellar clusters. And now you are going to see much better. This is a space telescope image in the I band. And the young stellar clusters, also forming a ring, are all these little nodes, bright nodes that you have in the circles. They are scattered here and there, and I think you guys see, you can disentangle well, one by one, all of them, okay? And again, they are within, not in the filaments of dust, these obscuring fingers, but yes, you notice a little bit, you pay attention, a little bit farther out or away from them or at the edges from this dust filament. So the clusters per se have very little extinction in the line of sight of the cluster. The dust is nest, but no within the cluster. We can again have the resolution enough to extract the light from each of these clusters to form the spectral distribution. Here are some examples. We go here from the infrared all the way, here is infrared all the way to the optical. And we get to the UV as well, I think, yes. And you see that the spectral energy distributions are also, in this case, contrary to the previous case, quite similar among each other. It's similar to the situation of the first galaxy, NGC 253, the starburst, nuclear starburst, but no, we are not going to see here multiple bursts of star formation. They all are fitting a very common, very similar spectral distribution with different amount of dust, but we can all of them getting similar ages. The ages are in the 3-4 million years, are very young. And again, because the range of ages is very narrow, we can derive once more a very short duration of this burst that happen at the same time very fast, 2 million years, over a kilopascal. We are again in a kilopascal region. The cluster mass are smaller, one order of magnitude smaller than in the previous cases. So no wonder that are far much fainter and it's more difficult to see them. This is not a very bright region of star formations. You had to dig a bit to see them. We have the cluster star formation rate again. We can measure, we have the mass of each cluster, the best duration. So is an order of magnitude below that in the previous cases, which is what we expected because the mass of the clusters is one order of magnitude less. So it goes fundamentally with the mass because the best duration is the same. So it scales down. Again, we have clusters of this mass in the Milky Way, similar star formation rate. So it's nothing particular or special, simply scale down with the mass. That's it. Just that here all have the same properties of mass, presumably size, we don't know, but mass and star formation rate and burst duration. Okay. And again, we can also count the number of clusters here. We have the mass, we can get a global star formation rate from the ring. And obviously it's going to be smaller than in the former cases. It's 4 times smaller because the clusters, the mass of each cluster is smaller as well. So it goes down accordingly, okay? I didn't show for this case the molecular gas, but I want to show you because, well, because we need to know where the molecular gas is. I showed you before in the previous case in 1097, it was this ring of molecular gas resolving various clouds, okay? Here, we have a kind of ring. The galaxy is a little bit inclined, so that's why it's It's really a bit more elliptical, this ring, but it's not one ring, it's several rings. We can have one, we can have another one, we have another one. So it's more resolved. Actually, it's because we have much higher angular resolution here than in the other case. So clusters here, the clouds here are around 100, 150 parsec size, but here we have the filaments and the clouds that are these point-like sources in which are regularly spaced in the filaments are radius of 20 parsecs. So that's why probably we can we see this molecular gas split in filaments, and the filaments itself subdivided in clouds, which are point-like. The little points you might wonder are the clusters, because we don't see the clusters, the light clusters only in the optical or in the infrared. We don't see in molecular gas. We wanted to see how they compare each other in location, and so this is why we put the little points here. These are the stellar clusters, and it was very interesting to do this because we noticed that by putting the clusters, most of them, they are in molecular voids. They are not in the molecular class. As logical, because these clusters, well, I don't know if very obvious. We always associate molecular gas with the star formation. Obviously, this is the case, but the clusters here are in many places with no molecular gas around, and that means that the parental cloud, where they come from, because they might come from a molecular cloud, it has been already evacuated. They have already got rid of it. They outflowed it from the cluster. And because the ages are very young, these are 3-4 million years, and we see clusters of 3 million years in voids, in molecular voids, means that this evacuation phase was also very fast, and it had to be in the range of less than 3 million years. So probably not even by supernova this happened, probably has happened by the winds of the first stars, not even the supernova have time to evacuate that. And most of them are in this situation. In that sense, they also they share this common property. The molecular clouds are these tiny bright regions that you see in some places that we can resolve. They form a ring as well as the ring of clusters. But these are what we interpreted as the new region from the new cluster, the new generation of clusters will come. We have the current one, and these ones are, in addition, we know they are gravitationally bounded, they are virialized. And we know we could infer the free fall time of each of these clouds are very similar also among themselves, are 10 to the 6 solar masses, all very similar size as well, and distributed along a ring. So we presume that these clouds eventually in the future, they are probably now in the fragmentation collapsing phase, are going to deliver a new cluster as the one we see now, and also along a ring, and probably with very similar properties among themselves, and perhaps very similar properties as the ones of the cluster we see now, in terms of mass, in terms of star formation rate, in terms of burst duration, simply because the similarity we see in morphology, or like the free fall time that we see them distributed in a ring. These are regions where are cooking the new clusters, okay? We do not have any optical counterpart or infrared counterpart of these clusters, so we do not exactly know in which phase are. Definitely must be really away from the zero mean sequence of star, but eventually they can happen. And the free fall time is around 10 million years, so we don't know exactly in which range now are of falling or collapsing are. But since we know the age of these clusters, the current ones, the active ones is around 4 million years, presumably nothing has happened. We do not see any new cluster, evidence, the star formation along the filaments in the molecular gas. Most probably, maybe we still need another 5 million years to get the new generation of clusters to come. So in a way, in indirect form, we also see a protocluster, a generation to come of protoclusters as we were seeing in 1097. Okay, in the former case I discussed. Okay, I wanted to show now how, to convince you how this segregation in between the clusters in the molecular gas is, and this is a nice image that illustrated. This is the red color is the same image as here, but now in blue is the molecular gas, the same one I showed you before. It's filamentary because it's a combination of colors to produce this image. You don't see that well, all the filament, the richness of the filaments, but you still might see how are distributed around the disk of the galaxy. And if you pay attention now, you see even more clear that the clusters, which we are taking directly from the image, are really in sections of the filaments which there is no molecular gas, or they are on the size of the molecular gas, but very few. You might see, well, here you might see the molecular gas on top, maybe by projection effects, I don't know, maybe it's correct, they are forming now, but overall, where the molecular gas is, you don't see any clusters, you see them more in this void. So there is a complete segregation, spatial segregation for most of them, and that tell us that, but they are close. They are close to the filaments, and that also inform us that this molecular material that we also see in dust here are channels in which material is flowing to the center, and flowing within the clusters to feed the clusters, to feed the new generation of clusters. So we need to have this material, not from these clusters, they already use it, but probably they form from material that came from the same filamentary molecular gas that we are seeing now. And you remember these filaments of dust, we could trace in this galaxy already from kiloparsecs distance in the disk of the galaxy. Okay, so I wanted to finish now with the feeding process of this filament. Basically I'm just saying now, but a bit to put the two galaxies that we can see more evident this feeding process of the nuclear star formation. Again, the galaxy I just talked before, just the last one, with all the dust filaments around in the disk of the galaxy, circularizing. Zooming on the central region, we see much better how they pass within the clusters. The same in 1097, here we have a dust lane. Here is more chaotic, how the rain of material falls in the ruin. Here is much more chaotic. Here is much more order. Dust lane here, a dust lane here, the entrance in the ruin here and here. So we try to see where we can have an estimate of the inflow rate of material across the filaments or across the dust lane, at least at the entrance of the rain. And because we have the dust map, we have the column density of material along these regions where we measure, we see the dust lane, and we have this association with molecular gas, where we have the dust, we see molecular gas on top, as I just showed you before. From the molecular gas, we have the velocity, we have the kinematics, and so we have kinematics, we have morphology, we have column densities, we can have relatively good estimate of the inflow matter along the dust lanes here at the entrance of the ring, or along some of these filaments. And this is what the numbers I put here. For example, here in the flow rate is around 2-3 solar masses per year, which compare with the star forming rate I just inferred before for this galaxy, the global one, summing up all the clusters, all the mass of the clusters that have been formed in the last burst, 4 million years. And so we need 1 million years, and we balance more than enough with the inflow matter we get through these dust lanes. And the same happened with this galaxy. we infer a much lower star forming rate. As I said, was 4 times lower than in the previous case, 2.2 solar masses per year. The inflow rate is much lower as well, but still from this filament, but still enough to balance the star forming rate that we have here. Actual, I mean, this is the actual star forming rate, and this is the actual, as it occurs now, inflow rate in both cases, okay? So this nuclear dust, these dust filaments, molecular dust filament that we can trace from kilopasses distance towards the center, seems to be the major suppliers of matter to the center. Okay, and it is supply of matter does not occur, is stopped, then presumably the star formation in the nuclear region is going to stop. And this is a very different view of the idea we always have with the feedback in star forming regions. Star forming regions outflow material from the supernova when they form, and this material that they flow from different clusters is returned to the medium, and then this medium with time start to cool down, and this is the new source of material to form new stars. That is a completely different thing here, because of the evidence from the morphology and tracing of the molecular and thus we see in the nuclear regions is a completely different thing. We definitely evacuate the clusters, the molecular gas they evacuated, they do it very well, but the major supply of material is obviously coming from this major source of income, filaments, long kilopascal scale filaments, and this is coming from the outer part of the disk of the galaxy, all the way, very well organized, all the way to the center. So they are the ones sustaining nuclear star formation. Okay, so I don't know if I went too fast or too slow, or but I'm concluding now. I try to show the parsec scale view across the electromagnetic spectrum is important, is crucial to separate star forming populations, star forming region populations. The nuclear star formation, even though we are, as I saw, different environments, including our Milky Way, show very similar properties. There is nothing particular special from the nuclear region. And it happened in bursts, many clusters. The bursts could be one single age or multiple age, but always on the same region. They are not spread in different regions. They are very fast. That is a very astonishing. 2 million years seems to be a tick time. Well, they all, even though they are separated by kilopasses distance, they know that in 2 kilopasses they have to be done, each of the clusters, with the forming adult cluster. And given a burst, the properties of these clusters are very similar. They show similar mass, similar baby size. I don't know, we cannot measure it for all of them, but for what we see in the Milky Way, they spread between 1 and 10 parsecs. Age, of course, is a burst, and star formation rate at the cluster level is very similar. And then something which I found curious is that this nuclear star forming region seems to be sustained by inflow material that come along these filaments, molecular gas and dust that come from large distance, well organized directly to the center. And obviously this matter stopped somehow. We might presume that the star formation in the nucleus will stop until new supply of material comes, if it comes. And well, that is all. That's it. Thanks for staying there.
Thank you very much, Almudena. Very interesting talks and results. So we have time for a couple of questions.
Okay, I have one. The usual. Well, first of all, Almudena, thank you very much. Beautiful talk and beautiful data and beautiful results. Very nice. I have a lot of questions. I'm gonna go in parts. First of all, can you tell me which models are you using to derive ages and masses? I don't think, maybe you mentioned, but I miss it.
The ages and masses are the properties of the clusters, all the clusters, where the basic ones are directly inferred from the spectral energy distributions that we build.
Yeah. But you are comparing with extrapolation models, I guess, and with dust models, no, for the emission of dust.
Yeah,
Yes.
the stellar population synthesis model. Yeah, exactly.
Yeah, but can you tell me which ones? Because I'm interested because
because
sorry.
we work with Gustavo Brusual, we had to use models.
Okay.
So,
Thank you. Now that was our data because I'm interested in
like it's okay.
and comparing several. So okay. So first question. Some of the masses you are deriving for the clusters, especially those for the NGC 1386, are actually very low, no? Or the order of 10 to the 3, you say, 5, 10 to the 3. Are you worried that could you have any effects of not sampling the whole IMF in these clusters and then maybe deriving like the Brown edges, the Brown properties?
We look at this Gladys, I think is in the audience. We study stochastic effects because, of course, the mass is small, and so maybe one single star can drive the whole business, the whole show. That is what we did in the paper. We found consistent edges, whether we were using a stochastic IMF by properties of the IMF. Essentially, you vary all what you want to have in the IMF to put it in the model, or with the standard way. And so we did not found a particular difference in all the properties of the clusters. So it seems consistent. It seems to be, there are differences, of course, but it seems to group within the values from the standard approach.
Okay, interesting. I'll have a look at the paper. Thank you. And another question. And did you find differences because you find like different masses in different galaxies, no? Like for the NGC 1380C, you say that the masses are around 10 to the 3. From the previous one, I forgot 10 to the 4, 10 to the 5, no?
Yeah.
And my question is, have you found any systematic difference or with I don't know, with external pressure or with metallicity or with something that can indicate that some properties is influencing the mass of the cluster that inside a galaxy seems to be very homogeneous, as you mentioned?
Yeah, no, we didn't look for any particular reason for the cluster mass. We get what we get. Some are more luminous, some are less luminous. No, not really. I cannot say why we have some more massive or not. I have some hint that perhaps because of the last thing I said before, if the inflow matter is less and a lower rate, then the system is a little bit lazy, you want. So with such a small rate of inflow mass, maybe you are not going to wait too long to form a very massive cluster. So you form what you can, and then you form smaller clusters. That might be an idea, but it's speculative. It's the thing I can see because there is a difference in the inflow rate definitely between the two cases. And then automatically the mass goes down.
Okay. Thank you. Interesting. Yeah. I was wondering because I mean the first one is maybe more metal poor because a little bit less massive galaxy in general. I'm not talking about the region or. Okay, but interesting. Yeah, thank you.
It could be there is a point with the metallicity. For any of the studies or characterization we did of the classes, we did not introduce metallicity.
The determination of the cluster, but you can maybe use the metallicity of the determined in the ionized gas, but for the center of the galaxy, right? Not necessarily for the clusters, no? Because I know that with set feeding it's very difficult to introduce the metallicity.
It could be that, but I thought at this point that maybe the simple one was the inflow rate, and the fact also that, for example, in the last one, we have many more clusters than in the previous because bursts have many clusters. The number of clusters are more or less about the same per burst, But in this one, we have 3 times more clusters, 3 times more, but less mass. So let's say, well, if I get less mass, I can try to produce many more of less mass. But
Okay.
this is a very simplistic approach, or maybe there are more physical reasons to have that.
No, but
In the
interesting.
Milky Way, we have the whole range as
Mhm.
well. That is more easy to study them in the Milky Way. In fact, Neil Evans studied a bit the star formation rate, revised the star formation rate in the Milky Way. He put an emphasis on the metallicity, the very difference of the metallicity across the galaxies. A paper he published some few years ago, 22, on star formation, review the star formation rate in the Milky Way.
Okay, I have a look. Oh, thank you very much.
Any other questions? I have one. I was wondering, you show the results for typical prototypical starbus, CPER-1 and CPER-2 galaxy. If I say it correctly, 2 of them also host an outflow. NGC, the starbus wind, and 1386 an ionized outflow. So I was wondering what is the role of the outflow in the formation evolution of the star clusters?
It's a supply of matter, rather hot, but a supply of matter. When I put all the galaxies around in the sample we study, we also study very active galactic nuclei, and we see equally star formation, younger and at different distances. So these outflows exist an outflow in 1386, definitely. Is in the starburst as well, mostly motivated not by the agent in the 253, because it's a very quiescent, something like in our Sagittarius A, in our Milky Way, by the way. But I think that what matters most is what is getting in already cold material, getting into the center, which is already cold. Okay, more than what it gets out. These outflows has been always used as a way to quench star formation in the nuclear region, but it's not the case. We have very active nuclei with a lot of star formation and very active in the central kiloparsecs, there moderately. So this quenching star formation, I argue a little bit with it because we see all cases. That is what the outflows would generate.
Okay, thank you. Do you think it could be interesting also to explore another field of view close to the one close to the center in this kind of objects? Because we are looking at a very inner region of the galaxies in the case of 1097.
But in 1097, the major star formation occurred where it is, where I showed to you, and outside in the disk there is not much going on. So you can feel.
Maybe in the bar structure.
But in the large scale arms, there is indeed a star formation. You see plenty of H2 regions. It will be, of course, good to know how probably they are fed by the same atomic gas as the gas in the dust laying down, and how is the star formation occur there. But I don't know, it has not been studied as far I know. We know the evidence of these star forming regions there. I don't know if the fans people are looking at that, but I think they are summing up a lot of light from many regions, not individually. So I wonder whether we have different populations of clusters. But this is why I compare with the Milky Way, because the Milky Ways have different environment, and then it will be, spirals will be a bit equivalent to what we have sort of with these large design spirals. And in the Milky Way, we have any time of these clusters as well, low mass, high mass. So it seems to be more freedom in producing clusters of different mass and properties, more than in the nuclear region. It looked like, but yeah. it will be interesting to do something in the spiral arms, for example, in NGC 253, that we have them to study how star formations there. We have a single population of different or similar ages, similar mass.
Okay, thank you very much. Well, any other questions? Well, if not, I think we can thank Almudena again. Thank you very much, Almudena.
Thank you. Thank you.
Thank you.
And thank you very much to all the people connected for joining us.
Thank you. Bye.
Thank you.
Thank you. Bye-bye.